Good morning. Good morning. Thank you so much for the opportunity. I hope you can hear me. Please just confirm if you can hear me.
And we can see your slides. Thank you.
Okay, awesome. I'm currently load shedded, so I do apologize in advance, but I think I do have enough battery and my Wi-Fi is okay to sustain me during this presentation. So today I am going to talk about power generation from a novel thermodynamic cycle using a zeotropic binary mixture and a low temperature heat source. But before I go into the presentation, maybe just a brief introduction of who I am. My name is Tobile Khawula. I am a Vitsi for life. So it's good to hear from some of my ex-supervisors and professors today. I worked at WITS on focusing on energy storage, particularly on the supercapacitors, developing electrode materials. So recently I have transitioned into the difficult side of power generation, which is thermodynamics. It is interesting and I'm enjoying it. So today I'm going to share a little bit about what we do at Cirrus Rehos and what we're up to, and hopefully it will be of big interest to all of you. Okay. So before I get into that, maybe let me just share what we do at Cirrus Rehos or why we do what we do. The goal here, we want to develop and mass produce and facilitate the global use of our technology, which is renewable power and water generation. We aim to provide our technology to eradicate energy poverty everywhere on the globe and quench the thirst of every living creature on the planet, whilst materially reducing the carbon footprint. So basically, hopefully this puts you in a picture of what we are about.
Sorry, Tobile, do you think you could make a presentation full screen?
Oh, sorry about that. Hope that has come through.
No problem. Yes, thank you.
Awesome. So we are interested in renewable power and renewable water. And what we have done, we have developed a groundbreaking technology that enhances the heat recovery to produce electricity. So for any power generation process or system, we know that the biggest challenge is the thermal efficiency. And a low thermal efficiency is a challenge in terms of power generation. Basically, we have less thermal energy that is being converted into electricity, and we want to change that. So we have developed a groundbreaking technology, and this is patented. And what we're doing is we are taking heat from the environment, and converting this into electricity. The company currently is focusing on, or previously the company was mostly focusing on the water generation, which was sucking air from the environment, condensing that using the absorption chillers to produce chilled water. This obviously goes through the purification processes. But now we want to change it around and generate electricity. So I'm just going to go into, basically this is using an absorption heat transformer and an organic Rankine cycle. So I will explain that later what it means. So in a typical power station, right, we burn coal to produce fuel, and that fuel is used to boil water, which then produces steam. That thermal energy goes into a turbine and is converted into mechanical energy, and the turbine is connected with a generator to produce electricity. That's how it works typically. And the cycle that is used in a power generation process is the Rankine cycle. And the efficiency of this Rankine cycle is about 40%. So the rest of the heat is wasted. So all the energy that we get from that cycle is 40%, the rest is wasted. So there's a lot of work that has gone into the subject in order to try and change that. And some processes or some power stations will have a bottoming cycle or a regenerative cycle, such as the ORC, in order to try and increase this efficiency. But a standard ORC still has a very low efficiency. So we still have a lot of amount of energy being wasted. So what we are proposing with the cycle with a groundbreaking efficiency value is that this could be used in a power station as a bottoming cycle to almost double the efficiency of the current power station. And that's what you have there in green, showing that the efficiency of our cycle is close to 70%. And I'll go into the details of how we got to that. So basically, what our technology is we've got two main components, the AHT, the absorption heat transformer, and the ORC. And these are coupled together regeneratively, and they're sharing a vapor absorption binary regenerator. So the heat input section consists of an absorption heat transformer, and a standard absorption heat transformer increases the temperature of the original source to a temperature that is higher than its source. And what this does is able to have a thermal energy powered heat pump, which is then absorbed, and it splits in the vapor absorption binary reactor, which is our distillation unit, before it is fed into the turbine in our ORC. So because the ORC, because the AHT and the ORC are connected to the VABR regeneratively, that is the reason why we are able to achieve a high efficiency of 70%. The advantage of this is that we are increasing the temperature of our source, which is a normal temperature for our cooling water that is rejected in a power station of 45 degrees. This is further increased and fed back into the turbine. Okay, so this is just a schematic showing our power cycle. I don't want to spend too much time going into this, but this is just to demonstrate how it looks like. And also the connection I've been talking about between the AHT, which is the evaporator part, and the ORC. In the middle here, we have our rotating packed bed distillation centrifuge, which is our endothermic process. So our working fluid is pumped from A into an evaporator, where the temperature is increased and fed back into the absorber before it goes into the turbine. A very small amount of heat is rejected in the condenser. As you can see here, we've got a valve where we can control how much of this we want rejected. If not, then we just are able to open the valve completely. So this technology, we have asked a third party to have a look to validate, firstly, its efficiency, because it's one of the most important things for the power generation. So we've had a look at all the process parameters at each of the process steps and confirmed that our efficiency is close to 65%, which is very similar to what we had originally predicted. And to do this, we used a mathematical model, which is called the RefProp, Reference Fluid Thermodynamic and Transport Properties, to have a look at the model as well as the process parameters for validation. So the last slide, I just wanted to share what this means in terms of our TS diagram and why is our cycle different to other standard cycles. So if you have a look here, we've got a black line in our cycle. We've got a blue line, and then we've got a red line. So for the black plot, we are showing a standard Rankine cycle. And for that, we look at, for the amount of heat rejected per cycle, we look at the AE line. And as you can see on the black line, which is a standard Rankine cycle, the line goes from all the way to there, which means that all the heat in a Rankine cycle is rejected in a condenser. In some cases, we've got a regenerative cycle where they have feed water heaters in the cycle implemented in order to try and increase the efficiency. And this line now has shortened a little bit. In our cycle, because of the temperature lifts that we have in our AHT system and the regenerative effect, we are able to reject very minimal heat, which then gives us a much better efficiency than what is currently existing. Okay, so yeah, that's all from me today. Here are my details on email. You can contact me. We are looking to collaborate as well to try and improve this work. Maybe it's also just worth mentioning that we are currently building a physical model in Cape Town in our plant to demonstrate this. We are almost at the end of building this model, and we're excited to test it and see it working. Thank you.
Thank you very much for a nice presentation.